Okay, today we're going to be doing Lecture 10. Lecture 10 is going to be on rational functions, and this is going to be part 1 of my 2-part lecture. All right, rational functions. So we're going to talk about what rational functions are, how they behave, and what the characteristics are of rational functions. So let's get started with the definition. Definition: rational function. Okay, a rational function is a function that has an equation of f of x equals a of x divided by b of x, comma, where a of x and b of x are polynomials. Where, of course, the variable is x, and b of x cannot be equal to 0. B of x cannot be equal to 0. So what a rational function is, it's basically a function that can be graphed on an xy plane. It has the equation f of x equals a of x over b of x, where a of x and b of x are polynomials, and b of x cannot be equal to 0. Now, why can't b of x be equal to 0? Well, imagine if you replaced b of x at the bottom with a 0. What would happen? You would essentially get, let me change my color to red. You would essentially get f of x equals a of x divided by 0 if I just let b of x be equal to 0. Now, if I have a 0 in the denominator, that means that I'm dividing by 0. And dividing by 0 is undefined for real numbers, so b of x cannot be equal to 0. It can be pretty much any other real number it wants to be, or any other real polynomial. It just can't be equal to 0. And let me put a note down, because this next note is going to be pretty important. So I'm going to just do a little parentheses and a note. Okay, note this. A of x and b of x, a of x and b of x, right, the numerator and the denominator, have no other common factors. Have no other common factors. Have no other common factors but positive 1. So what that means is a of x and b of x have to be factored as much as you can. And then if something is the same on the top and bottom, let's say they share a common factor on the top and the bottom, then you can cross those out. So this goes all the way back to rational expressions when we did Algebra 2 Part A, where you would factor the top and the bottom as much as you could, and then you could cancel out common factors on the top and the bottom, so that a of x and b of x, right, the numerator and the denominator, they have no other common factors but 1. So once you get rid of all the common factors, then the only common factor between a of x and b of x should be 1. Okay? And I'll leave that up there for a little bit so you guys can finish copying that down. But do know that the rational function is going to have a numerator and a denominator. So it's going to have a top of the fraction and a bottom of the fraction. And, you know, the top of the fraction could be 1. The bottom of the fraction could be 1. In that case, you would just be dividing by 1. but typically they're both going to be polynomials with a variable of x. So that's just a did you know kind of thing. All right. Let's go and talk about how to factor first, because I think a lot of kids have trouble with factoring the top and the bottom when we do rational expressions. So let's just go ahead to the next screen and let's do a really quick example. Okay, note. Before we start anything, you should factor the top and bottom. Note. Factor the numerator, which is the top of the fraction, and the denominator, and cancel out, any common factors other than 1. Any common factors other than 1. Positive 1. Okay. And I'll just put that as a note at the top. All right. Let's do a really quick example to show you how you actually factor the numerator and the denominator, and you can cancel out any common factors. So let's try this one. Let's say we're given a function f of x where the top of the fraction is going to be x squared plus 7x plus 12, right? And then the bottom of the fraction is going to be pretty much the same thing, but I'm going to switch up a couple of the numbers. We're going to have x squared plus 8x plus 15. So right here, we have a standard rational function. We'll graph this at the very end so you can take a look at what that looks like. But what we want to do first is, before we do anything, we want to factor the top and the bottom, and we want to cancel out common factors. So the way that we can factor the top is we can find two numbers that multiply to 12 but add up to 7. So what are two numbers that'll multiply to 12 but at the same time add up to 7? 3 and 4, right? So I'm going to write a 3 and a 4. So that way I can multiply to 12 but at the same time add up to 7. The bottom of the fraction has a 15. So what two numbers will multiply to 15 but at the same time add up to 8? What two numbers can multiply to 15? That would be 3 and 5, right? So I can break this up into a 3 and a 5. So then when I get done with it, I can factor the top with these two numbers right here, right? I can factor that as x plus 3 and x plus 4. There are many ways that you can factor. You probably learned it a different way than how I do it, but you will get the same result at the end. That's kind of the way math works, right? At the bottom of the fraction, I have a 3 and a 5. So I can factor this as what? X plus 3, x plus 5. X plus 3 and x plus 5. Making sure that you always put your factors inside parentheses, okay? That way you won't get confused with anything else and it won't be as complicated for you. So now that I've factored the numerator and the denominator, now it's time to cancel out any common factors that you may see. So what matches up on the top and bottom? The x plus 3, right? So I can cancel out the x plus 3 at the top, but I also have to cancel out the x plus 3 at the bottom since they match up. Because what you cancel out on the top, you must also cancel out on the bottom, right? Typical math sayings. Okay, so the top of my fraction is only going to be an x plus 4. X plus 4. And then the bottom of my fraction is only going to be an x plus 5. x plus 5. And of course, the denominator can never be equal to 0. And what that means is you can't divide by 0 at the bottom. So that's a very quick example on how you factor the top, factor the bottom. You cancel out common factors so that the only common factor between the x plus 4 on the top and the x plus 5 on the bottom is positive 1. Notice that the only common factor between the top and the bottom is positive 1, since nothing else could be canceled out. So that's that. Okay, I'll leave that up there for a few seconds and I'll keep on talking about it so I don't have any dead air time. But basically, for any rational function that you're given, you're going to want to see if you can factor the top and bottom first, because that's going to affect the answers that you're going to find on the next slide. So for every single rational function, we're going to be finding out basically 5 different characteristics, because rational functions are going to have what are called zeros. They're going to have vertical asymptotes. They're going to have horizontal asymptotes, oblique asymptotes, and maybe even point discontinuities. And that's one of those things that we saw when we did continuity. We saw that sometimes when you draw lines, you'll have a hole in the graph, and you can actually fill in that hole if you know what you're doing. Okay, so let's go ahead to the next slide and let's talk about the first characteristic of rational functions that you really should know. Okay, so on this slide, I want to talk about zeros. Now, a zero is also known as an X-intercept. So let's talk about them. Finding zeros, also known as X-intercepts. So I'll put that in parentheses. X-intercepts. So if you remember from Algebra 1, an X-intercept is where the graph is going to cross the x-axis. So these are points. These are going to be points x comma y, where the function or the graph of the function crosses the x-axis. Okay? So when it crosses the x-axis, those are called x-intercepts. They're also known as zeros. So zeros and x-intercepts, those are 2 different terms that basically mean the same exact thing, where the graph is going to cross the x-axis. So when you think of zeros, I also want you to think in your head of x-intercepts, because that's where the graph is going to cross the x-axis. Okay? A zero is going to occur. So zeros occur at each x in f of x equals a of x over b of x, right? Our rational function, where the numerator, a of x, is equal to 0. So what we're going to be doing is we're going to be taking our rational function. We're going to be taking the numerator, which is a of x, right? The top of the fraction, and we're going to set it equal to 0. So for the zeros, what you want to do is you want to set the top equal to 0. And we'll do a quick example from the last slide. Let's say we had that example where we had f of x equals x squared plus 7x plus 12 on the top of the fraction. And then let's say we had the bottom of the fraction being x squared plus 8x plus 15, right? And when we factored, we figured out that the top was x plus 3 times x plus 4, right? I'm basically just rehashing what we did on the last slide. So the top was going to be x plus 3 times x plus 4. and the bottom was x plus 3, x plus 5, right? Because we had to find those two numbers that multiply to 15 but add up to 8. Well, we know that the common factor on the top and the bottom is going to be the x plus 3. So we can cross out the x plus 3's, and what we're left with is we're left with x plus 4 over x plus 5. So what we're going to do with this function is we're going to find its zeros, the zeros. So I'll write out zeros. And the way you find the zeros is, remember, you have to set the top equal to 0. So what I'm going to do is I'm going to take the top of the fraction and set it equal to 0, and I'm going to solve it for x. So I get x plus 4 equals 0. Now, when I solve this for x, what I want to do is I want to get x by itself. So I need to get rid of the positive 4 by subtracting 4 from both sides. Subtracting 4 from both sides. And when I do that, I get x equals 0 minus 4, which is x equals negative 4. Negative 4. So that's where my 0 would be. So my x coordinate is going to be negative 4. That's basically the answer that I got, right? So I'm going to write my ordered pair. Now, when you write ordered pairs, you always put the x coordinate on the left side. So I'm going to put the negative 4 over here, and then the y coordinate will always be 0 because you're taking points from the x-axis. And remember, any point on the x-axis is going to have a y coordinate of 0. So that y value for that point is always going to be 0. It's never going to be anything else. But the x coordinate is going to be your answer when you set the top of the fraction equal to 0. So word to the wise, right? Now, what I want to do with this is I want to actually graph this, and I want you to see what it looks like on Desmos, because I feel like you can use Desmos to check your answer a lot easier than you can with a graphing calculator. Okay, so let's go ahead and hop on over to Desmos, and we'll graph this function and see what it looks like. Okay, so right here, I'm on Desmos. I put my inputs, my functions on the left side, and then on the right side, you'll see the XY plane, and the graph will show up there. So we had f of x, and when I graph these, I always graph it using my original function. So what did they give me originally? They gave me x squared plus 7x plus 12 on the top. So that's what I'm going to write on the top. And I'm going to do it in parentheses. You'll see why in a second. So x squared plus 7x plus 12, close up those parentheses, make sure they're closed up. And then what I'm going to do is I'm going to use the division symbol, which is basically just a backward slash. Okay, so what was the denominator? The denominator was x squared plus 8x plus 15. So that's what I'm going to put on the bottom in parentheses. So I'm going to start off my parentheses. I'm going to write x squared plus 8x plus 15, close it up. And this is what your graph is going to look like. That's that blue graph right there. And what I'm going to do is I'm going to change this color to black because I'm going to label the 0 in red. Okay? So what you'll notice about this graph is it basically looks like two U-shapes, right? Two parabolas that are on top of each other. And what we call this is we call this a hyperbola. A hyperbola. So that's what the graph shape is called, a hyperbola. And what I want to do is I want to write an ordered pair. So I'm going to go down to my next input, and I'm just going to graph an ordered pair. So what was the answer that we got from the last slide? That was what? -4, 0, right? Well, I can graph that in Desmos if I use parentheses. So we always use parentheses for ordered pairs, right? I'm going to graph -4, 0, just the point. I'm going to change the color to red so you can see it a little bit better. And there we go. This is the 0 right here. Notice that the 0 is just a point where the graph crosses the x-axis. So that's one way you can visually check what you did algebraically. Okay, and we can label this, we can even label this the 0. That's the 0 of the function. A 0 is just where the graph crosses the x-axis. Okay. All right. Let's head on back to our slide and let's talk about another characteristic of rational functions. Okay, let's talk about asymptotes now, because there are 3 different types of asymptotes. The first one and the most important is the vertical asymptotes. So let's talk about those. Now, you already know what a vertical asymptote is. I'd be surprised if you didn't. But they are imaginary dotted lines that we graph on the XY plane where the graph never crosses, okay? So the graph is going to get closer and closer to the asymptote, and it's going to start displaying asymptotic action, which means the values of the graphs just start going crazy up and crazy down, but the graph is actually never going to cross these lines, and they're called the asymptotes. Well, vertical asymptotes are going to occur at each x, in f of x equals a of x over b of x, a of x over b of x, where b of x is equal to 0. Okay, b of x is equal to 0. So what we're doing is we're taking the denominator and setting it equal to 0. We're taking the bottom of the fraction now. So notice how this is different from the last slide. In the last slide, we were talking about zeros, right? And that was when we set a of x equal to 0, the top of the fraction. Well, now we're setting the bottom of the fraction equal to 0, and we're seeing what happens. So just as an example that we've been working on, you know, we've been talking about this function for a while now. So let's find the vertical asymptotes of this function. The x squared plus 7x plus 12 on top. And on the bottom, we're going to have x squared plus 8x plus 15, right? And we know that we can reduce this down to what? X plus 4 over x plus 5, I think. Yeah. Once you cancel out all the common factors, you get x plus 4 over x plus 5, right? Well, now to find the vertical asymptotes, we're going to set the bottom equal to 0. And as I've talked about before, the denominator cannot be equal to 0 because you would be dividing by 0 right here, right? And that's a no-no. But what we want to do is we want to set the bottom equal to 0 and solve it for x so that we can determine where the bottom cannot be equal to 0. So what I do is I set the bottom equal to 0 and I solve for x. So for this one, I'm going to subtract 5 on both sides to get rid of that positive 5 on the left side. And then when I get done with that, I have x equals negative 5. And that's my answer. That's going to be my VA. VA, Virginia, right? VA is going to stand for vertical asymptote in this course. So what we're going to do is we're going to go back to Desmos. We're going to look at that graph that we found the 0 in, and we're going to make sure that the vertical asymptote is x equals negative 5. So let's hop on over to Desmos and let's verify this. Okay, so heading back to my function, I know where my 0 is. I know where it crosses the x-axis, but now I want to make sure that the vertical asymptote is x equals negative 5. So below here, I'm going to type in x equals negative 5, and I get this vertical line that divides the graph in half on the left side and the right side. So what I'm going to do is I'm going to change this color to blue, and I'm going to change it to a dotted line, because when we graph asymptotes, we always want to put them as dotted lines, right? And what you'll notice is both ends of the graph can get very, very close to this dotted line, but never actually cross it, never intersect it. So even if we zoom in and we keep on moving down and zooming in, we notice that the black line never crosses the blue dotted line. So that's how vertical asymptotes really work. They're these lines that the graph never crosses. Okay? That is vertical asymptotes. You just set the bottom equal to 0 and you solve for x. So I'll leave this up there for about a minute longer so you guys can get that down. But just know that you're taking the bottom of the fraction and you're setting it equal to 0 this time. Not the top of the fraction. That was for the zeros, right? But we're setting the bottom of the fraction equal to 0, and we're solving for x and seeing what we get. Okay. Let's talk about the next type of asymptote that you'll see in this course, and that's going to be the horizontal asymptotes, right? So we did horizontal asymptotes back when we talked about exponential functions. And we know that exponential functions have these things called horizontal asymptotes, but we also know that reciprocal functions, which are basically rational functions in disguise, they also have horizontal asymptotes. So let's talk about them. Now, these are not going to be as simple as the vertical asymptotes. I hate to break it to you. There are actually 3 rules that you need to follow with horizontal asymptotes. So let's talk about those 3 rules. Okay. Horizontal asymptotes. Rule number 1. If the degree of a of x is greater than the degree of b of x, there is no horizontal asymptote. There is no horizontal asymptote. There is no horizontal asymptote. So what does that mean? Well, degree just means the highest exponent, right? Degree means the highest exponent. So now we're looking at exponents, right? We're looking at powers, where you have a variable x and you have an exponent of n. Whatever number that highest exponent is, that's called the degree of the polynomial. So what we're saying is, if we have an a of x on top, let's say we have f of x equals a of x over b of x, we know that there's going to be a highest exponent on the top. We call that the degree of a of x. And we also know that there's going to be a highest exponent on the bottom, known as degree of b of x. And all this is saying is, if the top exponent is bigger than the bottom exponent, then there's no horizontal asymptote. You would just write none, because there's nothing to worry about there. But now let's talk about rule number 2. Rule number 2. What if the opposite is true? What if the degree of a of x is less than the degree of b of x? What happens? Well, if this happens, the horizontal asymptote is the line y equals 0, also known as the x-axis. Okay, so what does this really mean? Well, if the top exponent is less than the bottom exponent, then you're going to have a situation where you already know what the horizontal asymptote is, and that's going to be y equals 0, also known as the x-axis. So what's going to happen with these functions is that they're going to get closer and closer to the horizontal asymptote, but never actually crosses it. And we'll see an example of that in just a minute. But then we have a third rule, right? Can you guess what the third rule is? If the degree of the top is equal to the degree on the bottom, then the horizontal asymptote is the line y equals leading coefficient of a of x, so leading coefficient of a of x on top, leading coefficient of a of x on top, divided by leading coefficient of b of x on the bottom. Leading coefficient of b of x on the bottom. That is a b. I hope you understand that, because it might not be clear just looking at it since I kind of ran out of room. But what this is basically saying is if the top exponent and the bottom exponent are the same, then you're always going to have the situation where your horizontal asymptote is the line y equals leading coefficient of a of x over leading coefficient of b of x. So I'm going to keep this up there for a little bit, and then we'll talk about the example that I want to do on the next slide. So whenever you deal with horizontal asymptotes, you're always going to be following these three rules, and it's always going to be one of these. It's not going to be more than one, right? Whenever you're doing a problem on the classwork or the tests, you're going to be following these three rules for the horizontal asymptotes. You're going to be asking yourself, is the degree on the top greater than, less than, or equal to the degree on the bottom? So let's take a look at our previous example on the next slide. So let's say we had that example where we had f of x equals x squared plus 7x plus 12 on top. And let's say we had x squared plus 8x plus 15 on the bottom. Well, we factored this, we canceled out common factors, and now we know that the top should be x plus 4, and the bottom should be x plus 5. So now what we're going to do is we're going to identify the horizontal asymptotes, the HAs. Okay, so we need the degree of a of x, and we also need the degree of b of x. So once again, what is a of x? A of x is the top, x plus 4. Okay. What is b of x? That would be the bottom of the fraction, right? X plus 5. What is the highest exponent of x plus 4? Well, the highest exponent is going to be assumed to be 1, so the degree is going to be 1. And what is the degree on the bottom? That's also going to be 1, right? So we have a situation where these two sides are in fact equal. They are equal. So I'm going to put equal signs on all these. So if the two sides are equal, what do? Well, going back to our last slide, we know that the horizontal asymptote is going to be the line y equals leading coefficient of a of x divided by leading coefficient of b of x. So now what we want to do is we want to find the leading coefficient of the top, which is x plus 4. X plus 4, that's the numerator, But we also want to know what the leading coefficient is of the bottom. So I'm going to write leading coefficient of x plus 5. X plus 5. Okay. So when we do leading coefficient, what we want to look at is we want to look at the number that's out in front. So over here, I have 3x to the 5th power. I know that 5 is the highest exponent. So this is going to be the degree or the exponent, right? That's the small number above the x. But the number beside the x is going to be the coefficient. And sometimes I just write that as COEFF just to shorten it up. The number out in front of the x is called the coefficient. So we're going to be asking ourselves, what's the number out in front of the x? What's the number out in front of the x? Well, since there is no number, it's assumed to be 1, right? So I'm going to put a 1 right here and a 1 right here. And what that tells us is the leading coefficient of the top is 1. So I'll put a 1 on the top. The leading coefficient of the bottom is also 1, right? And then 1 divided by 1 would just give you 1. So my answer is going to be y equals 1. That is my horizontal asymptote, right? So that should be the horizontal asymptote that we see on Desmos when we graph it. So what we're going to do is we're going to hop back over to Desmos. We're going to see what the horizontal asymptote is, and we are going to verify that it is indeed y equals 1. So let's go ahead and hop on over. This is my graph. Remember, we have a 0 right here. We have a vertical asymptote right here. And I want to graph y equals 1 because I know that y equals 1 is going to be my horizontal asymptote. So let's type in y equals 1 and see what happens. We get this red line. And what I'm going to do is I'm going to change it to green. And I'm going to make it a dotted line because it's an asymptote. So this is my horizontal asymptote, y equals 1. Notice that on the right side, as the graph goes longer and longer to the right side, it gets closer and closer to the dotted line, but it actually never crosses. And you can even zoom in as much as you want to and move the graph to the right. And what you'll notice is that black line never crosses that green dotted line, okay? And the same thing happens on the left side, right? So if we move on over to the left side, the same thing happens. The graph starts to display asymptotic action as it approaches negative infinity. So the graph is going to get closer and closer to this green dotted line, but never actually cross it, right? That's how you know you're dealing with a horizontal asymptote. So that is horizontal asymptote. So I'll leave this up there for a minute longer, and then we'll talk about 2 more features that you might see for rational functions. Turn the page. Okay, so there are 3 types of asymptotes. There are vertical asymptotes. I'll put this up here in green. There are vertical asymptotes, right, where we set the bottom equal to 0. We have horizontal asymptotes, where we follow the 3 golden rules, right, looking at the exponents on the top and the bottom. And we also have the 3rd type of asymptote that we're about to talk about next, called the oblique asymptotes, the OAs. So these are going to be oblique or slanted. And that's what we're going to discuss on the next slide. Okay, let's talk about oblique asymptotes. Oblique or slanted asymptotes. I'll probably make a note of that. Now, these are the most rare type of asymptotes. You're not going to see these on every question, okay? And there's a reason for that, which we'll discuss a little bit later. But do note that oblique is just another word for slanted. So oblique means slanted. So these are going to be lines of the form y equals mx plus b, where m is the slope and b is the y-intercept. So going back to Algebra 1, we know that if we want to write something in slope-intercept form, we have to have y equals mx plus b, right? We all know that. So m is going to stand for the slope, and b is going to stand for the y-intercept. Okay? Now, oblique just means slanted, and slanted really just means this line is going to have some slope to it. It's not going to be a vertical line. It's not going to be a horizontal line either. It's actually going to be a line that has a slope to it. So let's talk about it. An oblique asymptote, only occurs if the degree of a of x is equal to 1 plus the degree of b of x. So this is a very hard and fast stipulation, right? The degree of the top has to be 1 more than the degree of the bottom. If so, you're going to have what's called an oblique asymptote. And the equation is y equals a of x over b of x, right? Top over bottom, with no remainder. So the equation of the line is just going to be the actual function, but with no remainder when you divide. And I'll show you what that looks like on the next slide. Okay, let me find one that has an oblique asymptote. All right, let's do this example. Let's say we have g of x is equal to x squared plus 4x plus 3 all over x plus 1. And by the way, this is number 3 on the problem set. Okay? So here we have a rational function where we have a numerator and the denominator. Now, I always start off by factoring first. And I know I can't factor the bottom, right? That's just x plus 1. We're going to leave that the way it is. But the top, we can factor that as 3 and 1. Because we know that 3 times 1 is 3, but 3 plus 1 is 4. That's how we get back to that middle term. So we can actually factor this top down as x plus 3 times x plus 1, where the denominator is still going to be x plus 1. That hasn't changed. The only thing that's changed is the numerator because we factored it, right? Okay, so what's the same on the top and bottom? What cancels out? Well, the x plus 1s are going to match up, right? So I can cross those out. And when I'm done with that, I have g of x is equal to x plus 3. So your graph is actually just going to be x plus 3. And that is the equation of the oblique asymptote. So your equation is going to be a of x over b of x, which in this case is just x plus 3. And this is the horizontal asymptote. And since there's no remainder, I wouldn't include the remainder even if there was a remainder, right? Because we're just taking a of x over b of x with no remainder. So this is going to be the horizontal asymptote of this function. So let's take a look at this function on Desmos and see if we can graph it. So I'm going to pop on over to Desmos, and I am going to, let's see, can I make a new graph? Yeah, let me make a new one. There we go. Okay, we're going to graph g of x equals x squared plus 4x plus 3 on top, and everything is going to be divided by x plus 3 on the bottom. No, x plus 1. Yeah, I think so. Is that right? Yeah, okay, I got it. So when I graph this, I don't get a hyperbola, I get a straight line. And this is the oblique asymptote, y equals x plus 3. And when you graph the oblique asymptote, which is just y equals x plus 3, you'll find out that they're actually the same line. They're the same graph. So I don't really need this. But this graph is going to have an oblique asymptote at y equals x plus 3. Okay, so that is oblique. And do know from the last slide that oblique means slanted. So your graph is going to have a slope to it. In that last case, the slope was 1, right? Y equals x plus 3. We know that the y-intercept with that would be 3. But the oblique asymptote will only occur if the degree on the top is equal to 1 plus the degree of the bottom. That's the only time that these rare asymptotes will occur, is when the degree of the top is equal to 1 plus the degree of the bottom. And once again, you just divide the top by the bottom, and then don't consider the remainder at all because it's irrelevant. What you're going to be looking at is what is the top divided by the bottom. Okay? And that is oblique asymptotes. Okay. Let's see. It is almost 9:40, and I only have one more thing that I need to cover. And then after that, I'll just be doing examples. So let's talk about the last feature of irrational functions before we go, because these are very important as well. All right. Point discontinuities. Point discontinuities. Discontinuities. I hope I spelled that right. I'm a math teacher, not an English teacher, so I don't need to worry about that. Okay, so talking about point discontinuities, we know from the continuity stuff that we talked about that sometimes you're going to have a hole in the graph. And it's as if somebody just plucked out a point from the graph and left a hole. That's what a point discontinuity is, basically. So let's talk about those. A point discontinuity at, let's say, x equals c, where c is a real number, occurs if x minus c is a factor, a shared factor of both a of x and b of x. So it has to be a shared factor, right? Those factors get crossed out. 4, f of x equals a of x over b of x, our rational function, which has a top and a bottom, where b of x cannot be equal to 0. Okay? So that's our definition. We know that the point discontinuity is going to occur at x equals c only if x minus c is a factor of both a of x and b of x for our rational function. So let's do the example that we did from the last slide. And I think we did g of x is equal to x squared plus 4x plus 3. And then on the bottom, what did we have? We had what? X plus 1. Good. X plus 1. Now, we know that when we factor this on the top, we're going to get x plus 3 times x plus 1. And we still have x plus 1 on the bottom. Right? So we factor the top, we cancel out our common factors, and we end up with just an x plus 3 on the top. So that's going to be our answer. But we want to find point discontinuities, right? So what we're going to do is we're going to take those terms that we crossed out, and we're going to set them equal to 0. So what I'm going to do is I'm going to set the x plus 1 equal to 0 and solve for x. Okay, so I take that factor that we canceled out, I set it equal to 0, right? Because that's going to have the missing point. I'm going to subtract 1 on both sides, and I get x equals -1. X equals -1. That's going to be my point discontinuity. So -1, comma, whatever my y coordinate is. Okay. Oops. Let me finish that. There we go. So at x equals -1, we're going to have a point discontinuity for this function. So let's see if we can identify this missing point on the graph. So going back to Desmos, I've already graphed my function g of x, right? I get a line. And what I want to know is, what is the function when the x coordinate is -1? So when the x coordinate is -1, and when we put in -1, we're going to have a y coordinate of, whatever we get. I know that it's going to be 2, right? This is going to be that point that's missing from the graph. So what I do with point discontinuities is I change them to holes. So I can change this from a point to what's called an open point, which is just a hole in the graph. And that's basically the point that the function kind of skips over. That's the point discontinuity. And the way I figured out what the y coordinate was I took the answer, which is x plus 3, and I let x be -1 over here. So let me change my color to blue. And what I'm going to do is I'm going to do g of -1. Now, g of -1, why am I doing that? It's because I know that my x coordinate is going to be this -1 right here. And if I try and figure out what g of -1 is, I'm going to find out what the y coordinate is. So all I'm doing is I'm taking this x plus 3 and I'm replacing the x with a -1. So I get -1 plus 3. What's -1 plus 3? That's going to be +2. So that's going to give me +2. So I know what the y coordinate is now. The y coordinate is going to be +2. So I'm going to erase this question mark right here, and I'm going to replace that with a +2. So it is at that point, -1, 2, on my graph where the hole is. That's where the point discontinuity is. And point discontinuities, they only occur at x equals c, only if we have a common factor that gets crossed out. We take that crossed out factor, right, that x plus 1, and we set it equal to 0 to figure out where the hole is in the graph. And once we got it, we can figure out what the y coordinate is by plugging it back in to our answer over here, x plus 3. Okay, And I'll leave this up there for a little bit so you guys can copy that down. But that is the fifth thing that you want to look for when you're graphing these rational functions. Okay? All right. I think second block is going to start at 9:50. So what I'm going to do is I'm going to spend the remaining 10 minutes of time just going over classwork questions, because I know everybody is going to have questions about the classwork and how to do them. So I figure let's just do one or two examples from the classwork, and then I'll leave the rest for you to do on your own. Okay? So let's take a look at the classwork. Let's take a look at the classwork. And then you'll know what to do on the test, right? I'll be doing problem number 1. All right, so let's work this out together. Now, let me put the directions up here. Ooh, that's a lot of words. Okay, for each rational function, what we want to do is we want to first, factor it, cancel out common factors. We want to find its zeros by setting the top equal to 0. We want to find the vertical asymptotes, which we find by setting the bottom equal to 0. We want to find the horizontal asymptotes using those 3 rules, the oblique asymptotes, if possible, point discontinuities, if possible, and then we want to graph the function on Desmos. So number 1, we're going to be looking at the function f of x equals x minus 2 over x minus 3. X minus 3. So looking at this function, our numerator is going to be x minus 2, and our denominator is going to be x minus 3. So we have what's known as a rational function. And rational just means fraction. You're going to have a top and a bottom. The first thing that we want to do is we want to factor the top and the bottom. And the top and the bottom are already factored. You can't really do much to them. So we don't need to factor and cancel out stuff. We can just go ahead and keep on rolling, finding the zeros, the vertical asymptotes, and all that stuff. So let's look at the zeros. Okay, so for the zeros, I want to set the top equal to 0. So I'm going to take the x minus 2 and set it equal to 0 and solve for x. So when I do that, I can add 2 to both sides to get rid of that negative 2, and I get x equals positive 2. So my point is going to be 2, 0. That's going to be my x-intercept, also known as my 0. Okay, so now let's find the vertical asymptote. Remember, the vertical asymptote is found when we set the bottom equal to 0. When we set the bottom equal to 0. So let's do that. I'm going to set the bottom equal to 0 and solve for x. So I get x minus 3 is equal to 0. I can get rid of that negative 3 by adding 3 to both sides. Adding 3 to both sides. And when I do that, I get x equals 0 plus 3, which is just 3. That's going to be my VA, my vertical asymptote. So once again, I set the top equal to 0 to find all the zeros, and then I set the bottom equal to 0 to find all the vertical asymptotes. Okay, let's move on to horizontal asymptotes. Horizontal asymptotes. Now, I want to know what the degree of the top is. So I want to know what is the degree of x minus 2. And I also want to know what the degree of the bottom is, x minus 3. Well, we know that the degree is always going to be the highest exponent. and that highest exponent is going to be, in this case, 1. So I have 1 on both sides. That means that the two sides are indeed equal. So that means I need to look at the leading coefficient of the top. So I'm going to label that as leading coefficient of x minus 2 on the top. And I'm also going to have the leading coefficient of the bottom, x minus 3. That's going to be the denominator. So what's the leading coefficient of x minus 2? Well, that's just going to be a 1 on both sides. So I'm going to get 1 divided by 1, which is just y equals 1 divided by 1. That would just be 1. That is my horizontal asymptote. And we'll see that when we graph it. Okay, let's move on to oblique asymptotes. Oblique asymptotes. So for oblique asymptotes to actually be a thing, you need to have the degree of a of x. You need to have the degree of a of x being equal to 1 plus the degree of b of x. This situation has to occur. Now, since the top has a highest exponent of 1, we know that the degree of the top is going to be 1. And we know that the degree of the bottom is going to be 1. So I have a 1 over here. 1 equals 1 plus 1, which means 1 equals 2. Obviously, 1 cannot be equal to 2, right? So I put not equal to, not equal to, not equal to. So there is no oblique asymptote that's going to occur. No oblique asymptotes. Because that stipulation, the degree of the top has to be equal to 1 plus the degree of the bottom. That stipulation must occur for oblique asymptotes. If that does not occur, then there is no oblique asymptote. Okay? And then the final characteristic of rational functions are PDs, point discontinuities. So are there any point discontinuities that we should be aware of? No, there are none. And that's because there are no canceled factors. There are no canceled factors. So for the last 5 minutes, what I'm going to do is I'm going to graph this function, and we're going to verify all of our answers. We want to find out where the zeros are. We want to find out where the vertical asymptotes are, the horizontal asymptotes, the oblique asymptotes, and the point discontinuities. We want to check all of this stuff on Desmos. So that's what we're going to do next. Okay. All right, that's my bell, so I got to make this quick. Let me delete this. So on the top, we have x minus 2. And close that up. On the bottom, we have x minus 3. X minus 3. And we have our graph here in blue, which I'm going to change to black just for our discussion. Okay, so what is the 0? Our 0 was just a point, right? An x comma y. That was 2 comma 0. So I'm going to graph 2 comma 0. Notice that this point right here, which I'm going to put in red, that is indeed the point where it crosses the x-axis. So that's my 0. I also want to label my vertical asymptote. Remember, our vertical asymptote was x equals 3. So I'm going to graph x equals 3. Perfect. That's my vertical asymptote. I'm going to change that to a blue dotted line. Good. Notice that it kind of matches up with the graph. The next thing that I want to graph is the horizontal asymptote. That's my next characteristic. So I move on over here. I know that it's going to be y equals 1 right here, right? Y equals 1. That's my horizontal asymptote. And that's my blue line right there. And I'm going to change that to green and dotted. So that's my horizontal asymptote. Notice that it neatly matches up with the function. And then the last two things that we talked about were the oblique asymptotes, which we don't have any, and point discontinuities, where we don't have any either because there's no cancel factors. And that is the function. That's the way you verify and analyze a rational function. So the two things that are going to be due on Sunday, once again, those were the rational function classwork, as well as the rational function test. The rational function test. So if you run into any snags, I'm going to be doing more problems on Wednesday. And if you happen to run into some trouble with any other questions, just send me an email. I will respond to you and we'll set up an office hours appointment. Okay? And I think that's all I wanted to talk about. So class dismissed. Oh, by the way, did you know yesterday was Pi Day? Yesterday was Pi Day. I know, we missed it, right? Pi Day, 3/14, March 14th. Well, today is what? Do you know? Today is the Ides of March. The Ides of March. So if you're a fan of Julius Caesar and a fan of Shakespeare, you'll understand where I'm going with that. Well, anyways, class dismissed. I hope everybody has a good day. Beware the Ides of March. Beware the Ides of March, Caesar.